All right, so this is the video for section 10.6. And in this, we're going to have more formulas to plug and stuff into. We're also going to get into having to solve some quadratic equations, which is what we went over before we did this chapter. So hopefully you remember that, but we'll review it here in a minute too. All right, let's first go over some vocabulary. And we've already covered this in this chapter, but they're just going to be more important in this section, so I wanted to cover it again just to make sure there was no excuse for not knowing what they are. All right, so segments of a chord. They're the segments formed from two chords that intersect in the interior of a circle. Okay, and then a tangent segment is a segment that is tangent to a circle at an end point. And guys, I believe in your notes, like right before here, or right after these, I'm sorry, there's a visual, a drawing of what each of these look like. So please do take note of that. A secant segment is a segment that contains a chord of a circle and has exactly one endpoint that is outside of the circle. And then, as you could probably guess, an external segment would be the part of a secant segment that is on the outside of the circle. All right, so the first theorem we have in this chapter is segments of a chord's theorem. Now, everything we're doing in this chapter is talking about length of certain segments. So this is when, and make sure you write, when chords intersect, or when, maybe I should put when segments intersect. How about let's put when segments intersect. Inside of the circle. So if you look down here, here's one chord, and here's one chord, and they do intersect on the inside of a circle, so we would use this. Okay, now I'm going to, so the green and the yellow make up one chord, and the blue and the purple make up another chord. Okay, and so I'm just going to label these A, B, and then X, Y. Okay, so this theorem tells us when two segments, when they intersect on the inside of the circle, you can find the length of one of these segments because A times B equals X times Y. Okay, so this segment times this segment is going to equal this segment times this segment. Okay, let's do an example. Okay, here, if I highlight the same segment the same color. Okay, so the two pieces of the yellow segment multiplied together are going to equal the two pieces of the purple segment multiplied together. So I can say X times 3 equals 4 times 6, or just 3x equals 24. X then has to be 8. Easy as that. Okay, let's look at B. Okay, so here's one chord, so the two pieces of this chord would be 2 times x plus 1, make sure you put that in parentheses, equals 4 times 3. Here, make sure we distribute through the parentheses, so 2x plus 2 equals 4 times 3 is 12. Minus 2, 2x is 10. X then has to equal 5. All right, let's do part C as well. So the two pieces of this chord is going to equal the two pieces of this chord. Now don't worry, it looks scarier than it really is. So I could say x plus 2 times x plus 1, that's going to equal x times x plus 4. Okay, so here, make sure we FOIL this. Okay, so we'd get x squared plus 3x plus 2. That's going to equal, here we have to distribute, x squared plus 4x. Now I know this looks scary, but take a look at this. Subtract x squared from both sides. Those would go away, those would go away. We get 3x plus 2 equals 4x, and that is an easy algebra problem. So minus 3x on both sides, you get 2 equals x, okay? All right, let's look at our next theorem. This is the segments of a secant theorem. Now this is used when segments intersect outside of the circle. Okay, and you're still going to be multiplying various segments together. Okay, now this one is commonly, the formula for this is commonly misused. Okay, lots of people wants to do EA times AB equals EC times CD. That is incorrect. Okay, that would be doing what we did last time, but we're not inside of the circle, so it has to be a little different. Okay, so what I like to teach that generally helps people remember is the double E. Okay, think double E here. When it's outside of the circle, when it's exterior of the circle, we do double E. And double E means it's going to be exterior times entire. Okay, so I'm going to go ahead, highlight this one yellow, this one purple. Okay, so on my yellow one here, the exterior is EA. So EA times exterior times entire. This is the entire. EA times EB equals exterior times entire. So exterior here, EC times the entire is ED. Okay, exterior times entire. If it intersects in the exterior of the circle, it's double E, exterior times entire. All right, so let's do an example. Okay, so exterior is 6, so 6 times the entire is 6 plus 9, which is 15. So 6 times 15 equals exterior equals 5 times the entire is just 5 plus x. All right, so 6 times 15 is 90. So 90 equals, we'd have to distribute this. 5 times 5 is 25 plus 5x. Subtract 25 on both sides. So this would be 65 equals 5x. So then x has to equal 13. Okay, now I'm going to help you set this up a little bit. So entire here is 9 plus 11. That's 20. And then the entire here, if this is 10, this is x, this is 10 plus x. Okay, I want you to go ahead and do B on your own, and then we'll go over it, and then we're going to do C together. All right, so you should have set this up. Exterior is 9 times entire, which is 20, so 9 times 20, should equal exterior is 10 times the entire, which is 10 plus x. And then when you do some algebra, make sure you distribute, you would get 8 equals x. All right, let's look at C. This one's a little more complicated. Okay, so exterior times entire. So this whole thing would be 3 plus x plus 2, which is just x plus 5. And then this whole thing would be x plus 1 plus x minus 1 plus 1 minus 1 go away, so it's just 2x. Okay, so exterior times entire. So exterior is 3 times the entire is x plus 5 is going to equal exterior is x plus 1 times the entire is 2x. Hopefully you can get to that. Okay, let's clean this up a little bit. So let's distribute through and then FOIL this over here. So 3x plus 15 equals 2x squared plus 2x. Okay, here the x squareds don't cancel out. We're left with an x squared, or a 2x squared, I guess. Okay, so now we have to use what we went over about solving quadratics. Okay, so remember, first thing we need to do is move everything to one side and set it equal to 0. So I'm going to minus 3x minus 15 minus 3x minus 15. So I get 2x squared minus x minus 15 equals 0. All right, so now remember, my a is 2, my b is -1, and my c is -15. So I want two numbers that multiply to a times c, but add to b. So my a times c is 2 times -15, so multiplies to -30 and adds to -1. Okay, that would be -6 and +5. Okay, so we're going to change this equation, 2x squared minus x minus 15, to 4 terms. So 2x squared minus 6x plus 5x minus 15 equals 0. Hopefully you're kind of sort of remembering this. Okay, the reason we do that is because now it fits in a box. So 2x squared minus 6x plus 5x minus 15. All right, so if I look up and down here and I pull out the GCF, all I can pull out is an x. Okay, so if the area of this is 2x squared, this is an x, this has to be 2x. And then if the area of this is -6x, this is 2x, this has to be a -3. Down here's 5x, this is x, so this has to be 5. And if I did everything correctly, 5 times -3 is -15, we're good. So my two factors here, 2x plus 5 times x minus 3, that's going to equal 0. And remember, this equals 0 when either this number or this number equals 0. So I can say 2x plus 5 equals to 0, minus 5, 2x equals -5. So x is -5 halves, or x minus 3 equals 0, so x then has to be 3. Now, if we plug a -5 halves in for x here, that would mean this length would be a negative. We can't have a negative length. So in the context of this problem, we can forget about this, and our answer would just be x equals 3.